Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here's the essay, Unnaturality, through Richard Dedekind, the number of real roots of algebraic equations. In the year 1883, Richard Dedekind, a titan of 19th century mathematics, cast his analytical gaze upon the seemingly straightforward problem of determining the real roots of algebraic equations. This endeavour, seemingly simple, was undertaken against a backdrop of ferment, a period during which the foundations of mathematics were being rigorously re-examined. The work itself, though perhaps less celebrated than his contributions to number theory, provides a fascinating window into the intellectual landscape of the era and the evolution of mathematical rigor. It demonstrates Dedekind's characteristic clarity and precision. To understand the genesis of Dedekind's work, one must first appreciate the state of algebra preceding it. The search for solutions to polynomial equations stretches back millennia, with the Babylonians employing methods to approximate solutions. The Greeks, notably Euclid, grappled with the problem in geometric terms. The Renaissance witnessed crucial advancements, particularly the solutions to cubic and quartic equations by Cardano, Ferrari, and others, laying the groundwork for a more general theory. The development of complex numbers, initially met with skepticism, provided a vital tool, the fundamental theorem of algebra, asserting every non-constant single-variable polynomial with complex coefficients has at least one complex root, began to achieve widespread acceptance. However, crucial questions lingered concerning the precise nature of the roots and methods for locating them. Dedekind was deeply influenced by the rigorous methods of his mentor, Peter Gustav Lejeune Dirichlet. Dirichlet, a pioneer in analysis, emphasized the importance of precise definitions and logical consistency. His work on the concept of function and the rigorous treatment of convergence directly shaped Dedekind's approach to mathematics. The spirit of Dirichlet, alongside the work of Cauchy, who rigorously defined limits and continuity, provided the groundwork for Dedekind to approach algebra with a heightened sense of precision. Crucial to Dedekind's thinking was his own prior work on the theory of ideals within algebraic number fields, a concept he introduced to address issues related to the uniqueness of prime factorization in certain number systems. He also made significant contributions to the development of set theory, particularly his definition of the real numbers using Dedekind cuts, a method that provided a coherent and rigorous foundation for the concept of a real number. Dedekind's specific contribution in the number of real roots of algebraic equations centered on providing clearer methods for ascertaining the number of real roots. He did so with a clarity of definition and a commitment to rigor then uncommon. Dedekind's approach focused on the application of Sturm's theorem, a technique for determining the number of real roots of a polynomial equation within a prescribed interval. Sturm's theorem, developed by Jacques Sturm in the 1830s, provided a practical algorithm for calculating this number. However, Dedekind elaborated on and refined the application of this method. He examined the properties of the Sturm sequence, a sequence of polynomials derived from the original polynomial and its derivative through a process of polynomial long division. By observing the sign changes within this sequence, one could determine the number of real roots located in a specific interval. While Sturm's theorem itself was well established, Dedekind contributed to the clarity of the method and the rigor of its application. He painstakingly verified each step, offering insightful clarifications. No detail was overlooked. The core of Dedekind's argument lay in meticulously analyzing the behavior of the Sturm sequence. He demonstrated in precise terms how to construct this sequence correctly, and, more importantly, how to account for the cases where the polynomials in the sequence might vanish at certain points, demanding careful attention to the signs of neighboring values. This constituted a refinement of existing methods and made them more reliable. Dedekind also clarified the relationship between the Sturm sequence and the roots of the original polynomial, showing how the sign changes in a sequence directly correspond to the presence of, or the absence of, a real root in the given interval. Importantly, he gave detailed explanations. The immediate impact of Dedekind's work, while not revolutionary in the sense of introducing entirely new concepts, resided in solidifying their understanding and application of existing techniques. It offered clarity and precision to Sturm's theorem, solidifying its place within the mathematician's toolbox. Researchers found his work helpful in their own investigations. The practical applications of his clarifications were felt most directly in the burgeoning field of numerical analysis, where accurate root-finding algorithms were of critical importance. Dedekind's methodical approach ensured the reliable application of Sturm's technique in practical situations. His careful analysis helped to avoid errors and potential pitfalls when applying the method to specific problems. Following its initial publication, Dedekind's work experienced a somewhat quiet reception. This did not reflect any criticism of its quality, but rather a prevailing intellectual climate. At the time, the focus remained on groundbreaking discoveries and the expansion of mathematical horizons. However, careful scholars acknowledged the importance of logical clarity and rigorous justification. Dedekind's work provided an excellent example of these attributes and served as a model. While his work might not have spurred instant major breakthroughs, it contributed toward the building of a stronger field. The influence of Dedekind's work on subsequent developments, while subtle, must be acknowledged. The focus on rigor, detail, and clear exposition had a lasting impact on the field, aiding further development. The rigorous methodology championed by Dedekind set a high standard that later mathematicians, even those not directly using Sturm's theorem, felt compelled to emulate. His meticulous approach influenced the style and presentation of mathematical papers for decades. This meticulous style played an indirect role. He also influenced the developing field of computational mathematics. The direct influence of Dedekind's work is evident in specific instances. His precise presentation of Sturm's theorem served as a foundation for future work on root-finding algorithms, particularly during the development of early computing machines. Individuals engaged in this area relied on Dedekind's clarity to navigate the complexities of Sturm's theorem. His detailed explanation saved time. Dedekind's work exemplifies a broader trend within mathematics: the gradual shift from an emphasis on abstract principles to rigorous proof. The quest for mathematical certainty became a defining characteristic of the era. Dedekind's contribution to this evolution should not be underestimated. He was a pivotal figure in establishing standards of mathematical discipline that continue today. He was meticulous. Dedekind's legacy, specifically regarding his 1883 work, extends beyond the immediate application of Sturm's theorem. He fostered an environment where clarity and precision became crucial. His influence can be observed in the work of mathematicians well beyond the subject of root finding. His ideas continue to impact how we approach problems. In conclusion, Dedekind's 1883 work, The Number of Real Roots of Algebraic Equations, may not represent the most dramatic of his contributions. It is representative of his commitment to rigorous exposition and precision. It played a vital role in ensuring the reliable application of existing mathematical tools. It is the product of a brilliant mind at the peak of its powers. Its impact, though perhaps less visually apparent than his work on number theory or set theory, contributes to the bedrock of mathematical understanding. His work helps to clarify what it means to truly understand mathematics.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.